Now we're going to look at derivations for means and variances of counts and proportions using some of the ideas we've already worked out for sums and averages. A lot of this derivation is in the reader in section 6. So here are two binomial distributions, spike plots of the probabilities of the count. What we need to do to get a binomial distribution probabilities is know the sample size n and the probability of a yes denoted by p. This is all we need to calculate binomial probabilities, so these quantities are called the parameters of the binomial distribution. The one on the left has the binomial probabilities for a sample size of 20 and a proportion of yes for the population of a half. And you can see that this distribution looks very symmetric around the value of 10. For instance, the probability of 5 yes is exactly the same as the probability of 15 yes. On the right, we have the binomial probabilities for counts, again for a sample size of 20, but now with a proportion in the population of only 20%. This distribution of the probabilities of the counts has quite a skewed shape. It's much more likely to get a small number of yes when the probability is only 20%. So to sum this up, one point we can make as we start to think about these distributions is that in general the binomial is perfectly symmetric only for a proportion p of a half. In order to work with means and variances for counts and proportions, we're going to use a clever set of random variables named after the members of the Italian-Swiss Bernoulli family. You may be familiar with the work of the Bernoullis from studies of physics. So we're going to set up random variables that I'll denote by a b sub I in honor of the Bernoullis. These are discrete random variables. Each b sub I takes on the value of a 1 with probability p and the value of a 0 with probability 1 minus p. So practicing in section 6 of the reader some of the theory we worked out for random variables in our week 3 materials, we could ask a question like, what is the expected value of b sub I? And that's simply going to be a probability weighted sum of the two possible values. So the expected value of b sub I is a probability weight of p on a 1 and a probability weight of 1 minus p on the value 0. And so of course this works out so that the expected value of the random variable b sub I is just equal to the probability of a 1 or p. What's the variance of b sub I? Well, now we have to subtract our mean off of each of our two values, square those deviations, and again take a probability weighted average. So the variance is going to be p times 1 minus p squared. That 1 minus p squared is the value 1 minus the mean squared. And then we have a probability weight of 1 minus p on 0, and 0 minus the mean gives us that 0 minus p squared term. And of course when we square that, we're just going to get the same as p squared. So we can simplify this a little bit. It looks fairly complicated, but each of those two terms in the sum has a common factor of p and a common factor of 1 minus p. So if we pull those out and use the distributive law, what we're left with from the first term in the sum is 1 minus p, and from the second term in the sum, just p. And so of course the expression I've put in the square brackets, 1 minus p plus p, is just going to be equal to 1. So the variance of one of these Bernoulli random variables, b sub I, is going to be equal to p times 1 minus p times 1. Well, so what? What are we going to do with these strange random variables that take on the values 1 and 0? Well, to set up the binomial distribution, each individual in the sample, or each binomial trial in the jargon you'll see used often, gets its own Bernoulli random variable b sub I. The number of yes in our sample is just the sum of the b sub i's. We get a 1 every time it's a yes and a 0 every time it's a no. And so the number of yes is just a sum of these. And if we carry out the binomial experiment of n trials many times, or for our applications we consider many random samples of size n from the population, we want to look at the question overall of these experiments or samples: what is the mean number of yes and what is the variance of the number of yes? And since we've set up these Bernoulli random variables, we can actually use some of our ideas from the previous sections to answer these questions. So here we go. Remember that the binomial setting assumed that every trial or every individual had the same probability of yes, or we might have said that the population from which we're sampling is homogeneous. So every one of these Bernoulli random variables is going to have exactly the same distribution. And I want to assure you that all of this derivation for Berkeley Biostat MPH students is in the reader in section 6. It's just sometimes helpful to have it talked through as well as reading it. Baldi and Moore do not give you the background you need to understand where the results come from. They just state them on page 296. And after you've walked through the derivations in week 4, you can rely on the statement, but you know you've seen the algebra behind them. So the mean number of yes is the mean of a sum of identically distributed random variables. So using the notation with the b sub i's for the Bernoulli random variables, the expected value of the sum is just the sum of the expected values of the b sub i's, and because they're all the same, that's just n times the expected value of one of them, which turns out to be n times p. So what we've done is take a look at the distribution of a sum of a binomial count, and it works out to be a function of the sample size n and the proportion of the population that is a yes or a 1. Now, to derive the variance of the binomial count, we need to use the independence of the b sub I, which is really important in applications that we're actually looking at a random sample from the population or random trials. But again, once we make this connection, the variance of the number of yes is the variance of a sum of independent, identically distributed random variables. And I've emphasized the independent because we're going to build that right in to the formula for the variance of the number of yes. So here we go. We have the variance of a sum of b sub i's, which by independence is the sum of the variances. And then again, because we've assumed we have a homogeneous population, every one of these Bernoulli random variables has the same variance. So that summation simplifies to n times the variance of one of the b sub i's, which is just n times p times 1 minus p, using the variance we worked out. So this is where the relationships work out on a variance scale. For our practical problems later in this week's materials, we're going to need the standard deviation of the binomial count, and so we just take the square root of the variance. The standard deviation of a binomial count is n times p times 1 minus p. So that's what's going on with binomial counts. We also want to talk about the sampling distribution of p hat, partly because for a lot of inference problems, sample proportions are going to be more useful than counts because proportions will allow us to compare samples of different sizes. That's important in applied work, but the way we're going to get at p hat is through the count. And of course, very important for our work, the sample proportion p hat is an estimate of the population proportion p. And continuing the new framework we've introduced, we're going to think about sample proportions from many, many samples. We take lots of samples and we just compute that one number, the proportion, and we look at the sampling distribution of p hat. And this does take a bit of getting used to. So when we talk about the sampling distribution of p hat, the other thing to keep in mind in week 4 is we're still working out sampling distributions by looking at the behavior of p hat in situations where we assume we know the population proportion p. That's what Baldi and Moore do in their presentation of these results in chapter 13. But let's assume that we're going to do that to take a look at the theoretical background. And then we're going to say, okay, given a proportion p and a sample size n, we're interested in 3 questions. We're interested in the shape of the sampling distribution, we're interested in the mean, and we're interested in the variance. And actually, we're going to answer the questions about the mean and the variance first, and then tackle the shape of the sampling distribution. So when we take a look at the mean and variance of the sampling distribution of p hat, remember that the sample proportion p is just the number of yes divided by n, and we're continuing to work with what's outlined in the reader in section 6. And so what we're going to say is that the sample proportion p hat is the average of these Bernoulli random variables. And of course, just like our work with sums and averages in the preceding sections, the average is a linear transformation of the sum. So we can apply the ideas we worked out early in this week's material about linear transformations. The expected value of p hat is the expected value of 1 over n times the sum of those Bernoullis. What happens in a linear transformation with a multiplicative constant like that is it just comes right outside the expectation, and we have 1 over n times the expected value of the sum. And of course we know then we have 1 over n times p. Okay, and so the 1 over n and the n are going to cancel out, and what we have is this very nice result that we've shown the expected value of p hat, again over all possible samples, is equal to the population proportion p. So to put that in words, the mean of the sampling distribution of p hat is the population proportion p. And remember, we said that when this works out, we're going to say that p hat is an unbiased estimate for the population proportion. So we had a similar property for x bar. Here it is also for p hat, because in some sense p hat is an x bar, just using these very convenient, clever Bernoulli random variables. So when we continue with this, Baldi and Moore just really state the results. It's all in the reader in section 6. The derivation of the variance of p hat also relies on our setup with the Bernoulli random variables. P hat is just a linear transformation of the count. So the variance of p hat is the variance of 1 over n times the sum of these Bernoullis. And it's important when you work with those linear transformation formulas for variances. This is 1 over n squared times the variance of the sum. So this is going to be equal to 1 over n squared, and then we'll fill in the formula we worked out for the variance of the sum, n times p times 1 minus p. So we're going to have a little cancellation. The n and the n squared will cancel out, and you'll often see the variance of p hat written this way: p times 1 minus p over the sample size n. And then, of course, to get a standard deviation for p hat, we'll just take the square root of the variance. So this is going to be a very useful formula for us. A few comments about this formula, just as we talked about with averages. The spread of the sampling distribution of p hat with this standard deviation, we can also write this, if we want, as the square root of the numerator, p times 1 minus p, over the square root of n. Putting it in this algebraically equivalent formula emphasizes that with that square root of n in the denominator, the sampling distribution is going to be more concentrated around the mean p for larger n. And again, everything we've done here for p hat is parallel to what we did for x bar to put us on a good theoretical foundation. So I hope listening to narrated PowerPoints can clear up some of the confusion that shows up in all those derivations in week 4. And these are facts that we're going to be using pretty much throughout our entire course about these very fundamental quantities, counts, and much more importantly, proportions from samples. So now you've seen where the formulas that Baldi and Moore state come from.